All right, so let's continue our discussion with support reactions. So let me just recap where we're at already. We've only had 2 lectures on reactions, and we've already covered quite a bit. We've assessed concentrated loads, we've assessed distributed loads, and those distributed loads, we've had uniformly distributed loads, we've had triangular loads, we've had incline loads, we've had pin boundary conditions, we've had roller boundary conditions, rollers that are perpendicular, rollers that are inclined. We've handled quite a bit. We're not quite done, though, because there's a couple other aspects of structural analysis we need to assess from a reaction standpoint. And so today we're going to focus on a particular part, and then Friday we're going to focus on the remaining aspect. And then next week we'll get into analyzing trusses. So what I want to talk about today are concentrated moments. Okay, so let me stop the share for a second so you all can see the whiteboard. So I have here on the on my whiteboard here, I have an I-beam, and I tried to draw it in 3 dimensions, and I have a beam framing into it. I just drew this as a block, just because a rectangular section, just because that was a little easier for me to draw. Now, up until now, we've handled concentrated forces or distributed forces. So if this was the beam I was looking at, you could handle, a load, like this, or, maybe a load, some sort of distributed load, something like that. But I wanted to show you sort of a real life situation where a concentrated moment might happen. There's a couple of instances. One of the I guess, physical representations of that is, let's say you have a member framing into this beam, but let's say that you're taking this member and you're twisting it. So this member is experiencing some level of twisting. Well, if this member is experiencing twisting, what this beam is going to see is a concentrated moment, right at that particular. So, if I'm looking at this beam as if it's some sort of, let's say supported section, I might have, my point load that I drew up there. I might have my distributed load right here. And then what I also might have is, let's say that being framed in right here, I might have a concentrated moment, like a single point moment right at that location. And so we need to be able to handle concentrated moments, not just from a physical representation like what we see here, but also an analytical one. What we're going to see as we, I went to share my slides. Well, I'll tell you what, we'll go ahead and share this PowerPoint. Let's do this. Like that. Okay, so we not only need to assess a reaction or a concentrated moment from a physical standpoint, but we also need to be able to assess it from an analytical one. Concentrated moments, and this isn't going to become clear right now, but later on when we start handling things like deformations, it will. But concentrated moments are going to serve as a powerful analytical tool for us later. For example, when you have a beam, let me stop my share here because I keep hopping back and forth, but I can't help it. So let's say I have, a beam, and I take a beam and I apply some load on it, and the beam deforms, it bends. Okay. Well, not only does the beam deflect, it actually physically moves downward, but it also rotates. So for instance, here's the beam and it deflects. You can see here, maybe I'll balance this on my shoulder. You can see here that, as the beam deflects, the beam was flat and now it's not. So it has an angle change to it as well. It goes down and it changes with its angle. That angle change, we call that a rotation. And in order to determine rotations later on, we're going to apply concentrated moments. So we need to be able to handle these, not just from a physical perspective, but from an analytical one as well. Now, let me go back to my slides. And so what we're going to do today are 2 different problems where concentrated moments come into play. The first one, which is what you see here on this slide, is just pretty much a regular old beam, but it has a point concentrated moment in that overhanging span. Our next example that we do after this is arguably a much more common representation of a concentrated moment, but between the two, you'll be able to handle just about any instance of this this happening in the real world. So we have a beam, it's an overhanging beam, and I threw some loads on here that we've handled before, you know, a distributed load and a concentrated load, but I also have a concentrated moment. So we're going to say we have a 20-foot kip moment, and it's being applied 10 foot from the right or to the right of support B. And so here's the structure. I'm going to give you a second to copy that down, and then I'll switch over to the notebook, and we'll chug this out. And if there's any questions, I mean, please, don't hesitate. For a short second, I almost grabbed my whiteboard marker and started writing on my surface. So I guess my coffee hasn't kicked in this morning. All right, I'm going to go ahead and stop the share and pull up the notebook. Here comes the cascade. There you go. All right. Okay. So here's the problem. Let me set my surface down. There we go. Get my power cord out of the way. Okay. So here's the problem that we had before. The first thing I'm going to do is I'm going to start to simplify some stuff with the problem. So let's see. Let's start off with my reactions. I'm going to go ahead and assume that both of my reactions are upwards. So we'll say this, or my vertical reactions, I should say. So this is AY, this is X. So we'll assume AX is going to the right. All that won't really matter too much here in a second. And so this is BY. So it's AY. I can draw that line a little bit. That's AY and that's BY. Okay. Second thing I'm going to do is I'm going to go ahead and idealize this distributed load that I have here on the left. I have 3 kips per foot over a distance of 10 feet. Hopefully by now this is becoming like pretty rote and pretty routine at this point. So 3 kips per foot over a distance of 10 feet can be idealized with a single 30 kip load, and then that distance is 5 foot. You can put 5 foot on this one as well. Okay. Everybody good so far? Any questions? Okay. Let me go ahead and make the page a bit bigger so that we can see a little bit more about what's going on. Okay. All right. So we've got 3 reactions we need to solve for. I'll go ahead and tell you that the concentrated moment in no way, shape, or form affects, for instance, your horizontal reaction. You're not going to handle that any differently. In other words, if I look at this structure and I sum forces in the X direction, I look at this and I don't see any forces acting to the left or to the right. So just with a lot of the previous problems that I've done, I can go ahead and just state that AX equals 0. So that should be pretty straightforward. What's left is to handle AY and BY. And so the way I'm going to do that, was there a message in the chat? No, I thought I heard a message in the chat. Okay, so the way that we're going to handle this is we're going to do it the same way that we've done in previous problems. We can sum moments at one support to determine the reaction at the other. So let's handle this like we've done before. Let's sum moments at A and draw our little table. And let's start, quantifying this out. So, start at the left, work your way over, and let's just do this like we've done every other problem. Do we consider the AX? No, because it goes right through A. Do we consider the AY? No, it goes right through A. What about the 30 kips? Yes, we consider the 30 kips. It would belong on the left side of the table because it causes a clockwise moment at A, and that 30 kips is at a moment arm of 5 feet. So 30 kips times 5 feet. Pretty easy. Okay. What about the BY? Well, do we consider the BY? Does it contribute moment? Yes. It's left side of the table or the right side of the table, it goes on the right side. And then we have a moment arm of 25 feet. So BY times 25 feet. Okay. So far, so good. That should be pretty rote. Now we get to the 20-foot kip moment. What do we do differently? Well, first off, does the 20, so we go through this process the same that we've done before. So let's ask those series of questions. Does the 20-foot kip generate moment at A? Well, yeah, it is a moment. So the answer to that question is yes, it does belong in the table. Second question to ask is, well, what side of the table does it go on? Does it go on the left side of the table or the right side of the table? And the answer is it goes on the left because it's a clockwise moment. I've got clockwise moments on the right, counterclockwise moments on the left, so it goes on the left. Now, the kicker is, what is the moment arm? Okay, because that's what we've been asking with the forces. We've said, the 30 kips, it goes on the left side of the table. It has a moment arm of 5 feet. The BY, it has a moment arm of 25 feet. And so you'd be tempted to ask that question, well, here's the 20-foot kips. It goes on the left side. What's the moment arm? But here's the thing. It doesn't have a moment arm. It is, in fact, a concentrated moment. Because it is a moment, you don't apply a moment arm because it's not a force times a distance. It's just a moment in and of itself. So what do? We just add that to the left side. It's just a concentrated moment. We're summing moments. We just add the 20-foot kips on the left. We do the same. Then we just keep on going and do the same thing with the 10 kips that we've done with our other loads. So this is 10 kips on the left times a moment arm of 25 plus 10 plus 10. That's 45 feet. And that's it. So the real takeaway from this is that whenever you're dealing with a concentrated moment, you don't multiply it by a moment arm. You just add it along with all of the other moments that you're summing, because it is in and of itself a moment. And that's really the only quirk to it. Other than that, it's handled the same way. So 30 times 5, that's 150. The 20, that's just 20. 10 times 45, that's 450. So 450 plus 150 plus 20 is 620, and we'll just use our shorthand foot kips, is BY times 25 feet. And somebody help me out in the chat. I'll start asking you all. What's BY going to be? Either with your microphone or the chat. Let's see. 24.8 kips, exactly right. So positive 24.8 kips, which is 24.8 kips going upwards. And then now that we've got that reaction, we have the AX, we have BY, so we need AY. We can sum forces in the Y direction. Now, do the same thing we've done before. So AX, do we consider AX? No. What about AY? Yes. Put that on the left column. The 30 kips? Yes. BY, we put that in the upward column, but we know what that is. It's 24.8. Now that 20-foot kips, do we consider that? The answer is no. We are summing forces. The 20-foot kips, that is a moment, okay? So we only consider that 20-foot kips when we're summing moments. So it went on the sum of moments at A expression, but it does not go here because it's not a moment. It's a force. Or because when we're summing forces in the Y direction, we're summing forces. We're not summing moments. So we can ignore that 20-foot kips because we've already considered it over here, and it's not a force. And so the only thing left is the 10 kips here, and that's all there is to it. So AY plus 24.8 kips is 40 kips. Okay. What do we got for AY? Somebody in chat. Now, this is easy, but I'm going to make sure everybody's awake. There we go, 15.2 and 15.2 kips. And since that came out positive, that means it acts upward. And so that's it. So AX is 0, AY is 15.2 kips upwards, BY 24.8 kips upwards. And that's it. That's all there is to it. I'm going to give everybody a sec to copy that down, and then if anybody has any questions, please, don't hesitate. Throw them in the chat. Turn on your microphone. I want to make sure this is clear. I don't want to just I don't want to move past something because the thing with this class, it builds on itself. So if there's something that was confusing at the on day 1, I don't want it to still be confusing on day 12. But I'll give everybody a sec to copy that down. All right. Let me stop the. Actually, I'm just going to pull this way. Okay. So this is the example we just did. Hopefully that was clear. Unless anybody has any questions, we'll go ahead and move on to our second example, which is to look at cantilevered beams. And here's the thing. Cantilevered beams are incredibly common in structural engineering. Anytime that you have a balcony, anytime that you have, for instance, like a bridge pier, like for instance, if I'm looking at this pier right here, I can idealize that as, as a cantilevered beam right there. This part right here, I can idealize that as a cantilevered beam. And so what I mean by a cantilevered beam is I'm talking about a segment where I have a beam and it's supported by, some sort of fixed support. And so we haven't handled fixed-ended beams yet. We haven't handled that fixed support, but they're incredibly common in structural engineering applications, and we need to assess them. Fortunately, while they're common, they're pretty easy to analyze. All of the reactions are all at that one end, and so we're a bit freer from an analysis perspective on how to solve for the unknowns. We don't. In the last problem that we did, there was some strategy to it. So we look at this problem. We summed moments here because this reaction and this reaction went through it. And so we summed moments right there so that we could obtain this reaction. And so there was some strategy as to why we did the problem in the order that we did it. With cantilevered beams, that kind of goes away. If you have a beam that just has a fixed support on one end, you can kind of solve for any of the reactions in any order, and it doesn't really matter. But the thing you need to recognize is that there are 3 reactions at that fixed support. There's a vertical reaction, there is a horizontal reaction, but then there is also a concentrated moment. There is a concentrated moment reaction anywhere there is a fixed support. And so hence why we're talking about that today. The theme today is to handle those concentrated moments. Okay, any questions? All right, so today, so our second example, and this is our last example for today, so we might actually end a little bit early, and that's completely fine, is I want to look at this cantilevered beam. I went ahead and threw an incline load on there just to sort of mix it up a bit and add some of the concepts that we've been working on for the past couple days, but I've got a cantilevered beam and I have a 20 kip load at the free end. and then around the middle of the beam, I have a 10 kip load, but it's at an incline. It's at a 3-4-5 slope ratio. And so we're going to have to break that up into X and Y components and then ultimately solve for our reactions. But I think you're going to find this is pretty straightforward. Okay, so let me get out of this, go to my OneNote, break that down a bit, and let me do this. Okay, so here's the problem. First thing that we need to do before we handle any of the reactions is we need to take this 10 kip load and we need to break it apart a bit. So first off, we have this triangle here. This is a 3, 4, and this is going to be a 5. That's a 3, 4, 5 triangle. And so what that means is I can take this 10 kips and split it up into a vertical force and a horizontal force. I can break that up into its components. And so the vertical force, so let me do this over here on the side. So the X and Y components are going to be, 3/5 of 10 kips, which is, 3/5 of 10 is 6, and 4/5 of 10 kips is 8 kips. Well, look at my slope ratio. The 4 is bigger than the 3. The 4 is associated with the vertical, so this is 8 kips. This is 6 kips. And then I've got my 20 kip load over here, which I don't really need to do anything with. But what I do need to do is, here, let me move this over a bit. Oh, sorry. Just so I got a little bit of room. Actually, move that over just a tad, so I got a little bit more room. Okay. I do need to indicate my my reactions over here at A. Now again, A is a fixed support, so I'm going to have a vertical reaction. So we'll draw that upwards. We'll call that AY. My horizontal reaction, I am going to have a horizontal reaction. We'll do that, let's say to the right. We'll call that AX. And then we are going to have a moment reaction. Now, again, you can assume any direction. I'm going to go ahead and assume that it's going this way. Again, it doesn't really matter. You can assume the other direction. And just like with all other reactions, if you get a negative answer, that just means you assume the wrong direction and it acts, if you assume clockwise and you get a negative answer, that means it acts counterclockwise. That doesn't mean that you did anything wrong. So, MA. Okay. All right, any questions? All right, so, sorry. Okay, so we've got these 3 reactions we've got to solve for, and one of the things I had mentioned is that it actually doesn't matter what order you solve them in. You can solve for the X direction, the Y direction, the moment reaction. You can solve for them in any order because all of them all coincide at the same point. There's no real strategy. You could just start going through the equations one at a time. So that's what I'm going to do. I'm going to start off with sum of forces in the X direction. And I'm going to go ahead and just draw a table out just to be consistent. So I look at the structure. I have AX. I have that drawn over here going to the right. I have 6 kips. I have 6 kips going to the left. And so that's it. So AX is positive 6 kips, which is 6 kips to the right. Like I said, cantilevered beams, they usually are pretty easy. If I sum forces in the Y direction, let me scroll down a bit, give me a little more room. If I sum forces in the Y direction, so what do I have? I have AY going up. I've got 8 kips going down. I've got, what is that, 20 kips going down. So that's it. AY is 20 plus 8, it's 28. Now, for the sum of moments, what I am going to do is I am going to sum the moments at A. You could sum them anywhere, it really wouldn't matter, but I think that summing them in A is just pretty easy. And so we just start and work our way over. So we don't have to consider AX. We don't have to consider AY. We do have to consider this MA. And right off the bat, in case anybody is confused, what this equation here means is that I am summing moments at A. This is a moment reaction at A. So I'm calling it M sub A. Maybe that's not the best name for it. Maybe it should be, you know, reaction moment at A, whatever you want to do. I just use MA just because it's kind of shorthand for me. But you know, just so you know that those aren't the same thing. So I've got AX and AY. I don't have to consider those, but I do have to consider the MA, and I just put that on this side because I've got it drawn counterclockwise, and it's right there at A. And then everything else I just handle like I've done throughout the semester. So the 8 kips, I've got the 8 kips generating clockwise moment at a moment arm of 10 feet, and then I've got the 20 kips generating moment at 20 feet. And so 8 times 10 is 80. 20 times 20 is 400. So 400 plus 80 is 480. So therefore, the moment at A, that comes out positive 480 foot kips. And so that equals 480. And if you want to use your shorthand symbol, foot kips. And then draw your direction. And your direction is going to be, you know, like that, because that's the direction that we assume. So it'd either be that or that for your moment reaction. So AX is 6 kips to the right. AY is 28 kips up. MA is 480. Hold on. Foot kips like that. Move that back up so everybody can see that. All right. And that's it. That's pretty much all there is to it. I'll give everybody a sec to copy that down, and then I want to see if anybody has any questions. I do want to show you something on your homework assignment. I want to try and there might be I foresee a question coming up, and so I want to kind of see if I can reduce some of the confusion. But I'll give everybody a sec to copy this and see if anybody has any questions. All right, let me tilt my screen back up so I can kind of see what I'm doing here. All right. Okay, let me stop my share real quick. Give me 1 second. So on your homework assignment, you were assigned 2 problems, problem 3.9 and problem 3.11. I want to pull those up because there's something I want to indicate about one of them. Give me 1 second. Okay. All right, give me 1 second. Here we go. All right. So here are the two problems, or here's one of the two problems. I think this one's going to be pretty straightforward. In order to determine the reactions, it's just a cantilevered beam. It is in metric, but I thought it was a really good problem to illustrate a lot of the things that we've been working on for the past few lectures. So I really liked this problem, and I also think it's going to be pretty straightforward. But this is problem 139. This is problem 2, and I want to show you something with 3-2. First off, if you notice, the beam is haunched. It has a variable depth. So, you know, like at point A, the beam looks a lot deeper. It looks a lot deeper here than it does right here. For the purposes of the problem, that doesn't matter. You could just treat it as if it's just a single beam. It won't affect your answer. It won't affect anything. That won't matter. But I do want to talk about this part right here, because you kind of have this like distributed load, it's uniform, and then it kind of turns into a triangular load. And so I kind of want to illustrate like how you would handle that on the board real quick. So let me stop my share here. Okay, so here's the problem. So it goes like this. Here's the beam, and then you have something that goes like this. Okay, and they say here that this is 3 kips per foot, and they say that this is 2 kips per foot. Okay, and for the sake of discussion, let's just say that ends, I don't know, right here. Okay, and so the beam goes on, just keeps on going. And so I think we have like a support right there, although that really doesn't matter. And so we have this, you know, distributed load, kind of goes like this, and then goes like that. Okay, so what I want to recognize is that, you know, this magnitude here is 2 kips per foot, and then this magnitude is 3 kips per foot. Okay. So the way to handle this is, you know, if you can handle a distributed load and you can handle, or a uniform distributed load, and you can handle a triangular load, then you can handle this by just splitting it up into its components. Okay. So what I'm going to do is I'm going to say, okay, let's, let me delete some of these arrows inside to make it a little easier to see. Okay, so what I'm going to do is I'm going to sort of just imagine a little line right here, and instead of this weird funky load, really all I have are 2 loads. I have one distributed load, okay, and I think this might be something like, don't quote me on the numbers, but I think this might be something like 30 feet from here to here, and then this might be something like 10 feet. Okay, so I've got sort of 2 loads. I've got this uniformly distributed, and then I've got this triangular load right here. So let's just sort of shade that in so it looks a little different. Now, the big thing to keep in mind is the magnitudes. Okay, and so if you think of this like a rectangle and a triangle, and you're trying to determine the area, you got to ask yourself, what's this and what's this? Okay, so this is 2 kips per foot, so this is 2. And if this total height is 3, then that is 1, right? So if you're idealizing this as a point load and idealizing this as a point load, you know, if we're talking about this triangular load, it'd be 1/2 of 1 times 10, and the rectangular might be 2 times 30, okay? But again, I mean, it might look a little funky, but it's no different than any of the other loads that we've handled for the past few lectures. Does that make sense? Anybody have any questions on that? I had a feeling that, like, as I picked the problem, I was like, oh, that might be a little funky. So let's take some time and go through that. Any questions? right. Well, hey, it's 10 minutes early. We're getting off early. What we're going to do next time is we're going to assess the final quirk, if you will, with reactions, and that's an internal hinge. And that one, I don't want to say it ramps up the difficulty, but the problems do get a bit longer because there's a little bit more going on. You have to cut a section, you have to look at the internal forces, and so there's a little bit going on with the next lecture. So we're going to talk about internal hinges next time, and then that's pretty much all we have for reactions because there's really not much else to say. That's everything. Next week we'll talk about trusses and you know, go through method of joints and method of sections, and so that'll be our schedule for the next little bit. I'm going to go ahead and stop the recording. That's all I have, everybody. Have a great day. We'll see you on Friday.